Hello everyone and welcome back to Power Electronics Lectures. In today's lecture we'll talk about the controlled rectifiers. At the beginning of the year we talked about the rectifiers in general. We didn't talk about the controlled rectifier. We talked about the uncontrolled rectifiers where we use diodes to convert the AC waveform to a DC waveform. And we don't have much control at that time of the voltage or the amount of the energy that we can transfer. For example, the half-wave rectifier, we just transfer the half of the wave from the input to the output. For the full-wave rectifier, we transferred the full wave. Do we have something in between? We don't have any something in between. We don't have 1.5 full-wave rectifier. Right? We don't have something like this. But in the controlled rectifiers, we will use devices such as the thyristors to control the waveform, okay, the AC waveform, and convert it to a DC waveform. If you think about the controlled rectifiers, you will find that controlled rectifiers can be divided into two main categories. Number one, what we call the single-phase rectifier. And number two is three-phase rectifier. For each one of these, we have half-wave rectifier and full-wave rectifier. Half-wave and full-wave. And here also we have half-wave and full-wave. But this half-wave and full-wave are different from what we studied previously. It depends on the firing angle. We'll study now what is the firing angle. Okay, it depends on the firing angle that we apply on each of these rectifiers. So this half-wave means the maximum can be half-wave, but we can control with it and send, for example, a quarter wave. Here we have the same thing. Full wave, the maximum is full wave, but we have the option to change the firing angle to make it maybe quarter or 3/4 or so. So the main idea here, we have an AC waveform, okay, that's coming from the AC line, and the output is should be converted to a DC, but here we have control. We have power to change the amount of power or the amount of energy that's transferred from the input to the output. And the most important part here, when we convert from AC to DC, you will find that we need to care about the input current here. We need to make sure that the input current is in phase with the input voltage, or the input current should be like a sine wave. Sometimes the input current will be a square wave, which means loads of harmonics, okay, and these harmonics are injected to the grid, which is not good. So we need to think about these issues to improve the quality of the grid, okay, or the quality of the power system that we have. So it's not easy just to convert from AC to DC, because most of the time you'll find that your current, the input current that's coming from the grid, is distorted, has a lot of harmonics, and these harmonics must be removed. Let's have a look at the input waveform here and see what are the differences between this controlled rectifiers and other type of converters. Okay, we said last time when we studied the inverters and the power converters, we have a transistor, and here the transistor receive a signal, a pulse width modulated signal from a controller. And we said this pulse width modulated signal, it has what we call a switching frequency. But this switching frequency for the power inverters and the power converters is a high frequency, like 1 kilohertz, 10 kilohertz, and so on. It's a high frequency, not a line frequency, not 50 hertz. But the case is different for the controlled rectifiers, for the AC to DC rectifiers. Here, we will care much about the pulse, the firing angle, that is related to the 50 hertz frequency. So we will not study this one. Now we will use something we call the thyristors. And these thyristors receive signal. The gate signal is, the frequency of this gate signal is proportional to the line frequency. Okay? Which means 50 hertz, 60 hertz, like that. Okay? Not 1 kilohertz or 10 kilohertz or so. These devices are very slow. Yes, they can handle high power, high current, but they are very slow. We can send like a 50 hertz signal, no problems. So what we do actually is to send this signal to this thyristor, to enable this thyristor. We have a sine wave, and we need to synchronize the sawtooth, our sawtooth here, with the sine wave frequency. This is 50 Hertz, so the duration from here to here must be 50 Hertz. This must be T. And here, T over 2. And the amplitude of the sawtooth is, let's say, 1, or we can say V sawtooth. Now, there is a relation between the firing angle that we send to the thyristor and the amplitude of the sawtooth. So if we say, for example, here this is T1, okay, if we say T1 over T over 2, so the relation between this time, the firing angle, the signal that we send it to the thyristor, and the whole period here, which is T over 2, this should be equal to how much? The reference signal, which is this line, V reference, over the amplitude of the sawtooth. So T1 over T over 2 is equal to V reference over V sawtooth. Now do some arrangements here. You'll find that T1 is equal to how much? T times V reference over 2 times V sawtooth. And if we multiply this by 2 pi to get the angle, not the time, so 2 pi times T1, which is alpha, let's say, the firing angle, this will be how much? 2 pi, 2 will go with 2, so this will be pi times V reference over V sawtooth. So we have to divide by T, by the way, so this will be the firing angle, either using seconds or degrees, no problems. Now revising the working principle for the thyristor, how the thyristor works. Now if we apply the voltage on the thyristor will be ready to work, but still waiting the signal. If we send signal to the gate, the firing angle, then the thyristor will start conducting like the diode. Even if we have positive voltage, even if this thyristor in the forward bias, but without signal it will not work. We have to trigger the gate. Once we send this signal, at this time you'll find that thyristor starts conducting. Now if we remove the signal, the thyristor will keep conducting. Why? Because it is a huge current. We cannot stop the huge current. There are two ways to stop the thyristor. Either the current inside the thyristor reach to 0, or if we reverse the voltage on the thyristor. And sometimes if we still have current inside the thyristor will never stop, will be conducting. Similar to the diode. The diode, if we have current, even if it's in the reverse bias, if we have current inside the diode, then the diode will keep conducting, right? Same thing will happen to the thyristor. If we have current inside the thyristor, so the thyristor will keep conducting. Now let's move to a simple circuit, which is a single phase half wave controlled rectifier with R load, or how things working. So now we'll focus on the single phase half wave controlled rectifier with R load. This is a very simple circuit. The input is an AC waveform. So here we have AC waveform. This is V input, and here we have the thyristor is connected between the source and the resistive load. And at this point here, from here to here, this is alpha, the firing angle, which means we send a signal at this point. We have signal to the gate of the thyristor. If you look at this portion here, the voltage is positive. The voltage that is applied on the thyristor is positive. But from here to here, there is no conduction, right? There is no conduction because there is no signal sent to the gate. Once we send signal to the gate, you'll find that what happens? The thyristor starts conducting, and the output voltage will be exactly same as the input voltage. So this portion will be exactly same as the input. Now, at this point, once the input voltage reaches to 0, then you'll find that the thyristor will be off. Why? Because number one, there's no current inside the thyristor, and number two, the voltage applied on the thyristor is equal to how much? Is equal to 0. You will find here the thyristor is off. Now, because here we have a resistive load, then you'll find that the output current will be similar to the output voltage, right? And the voltage, the thyristor voltage here, will be how much? V input minus V output. So this portion minus this portion, right? So this is the thyristor voltage. And the output current here, I out, it will be similar to the output voltage. Okay, the shape of the waveform, it will be similar to the output voltage. At the negative half wave here, the input voltage is negative. So the thyristor by default will be off, right? It will not conduct. Even if you send signal, there's no conduction because we have negative voltage, and the thyristor will never conduct until we reach to the next firing angle here. When the input is positive and we have at certain point a firing angle or a signal sent to the gate, then the thyristor will conduct. So now our target is to find the average voltage here on the output. Okay, we need to find this average voltage. We'll see, is it really half wave or quarter wave, or what's the value of this, okay, of the output voltage. Okay, so if you try to calculate this voltage, you'll find that V out is equal to how much? The average integration from T1 until T, from this point until T, V maximum sine, sorry, until T over 2, V maximum sine 2 pi T over T dt. And we have to divide by 1 over T. So here, to find the average for this portion, the average with respect to what? With respect to the whole period, which is we have to divide by T, right? But the integration from here to here, right? From T1 to T over 2. We need to find this area and divide by the whole period T. So integration for sine what? Minus cosine. So this will be minus cosine 2 pi T over T. And this will be from T1 to T over 2. V maximum is constant, will be out. So this will be V maximum over T, capital. And here, if you try to substitute this one here inside the cosine, you'll find that this will be 1 plus cosine 2 pi T1 over T times V maximum over T 2 pi. And we can say that 2 pi T1 over T, this is what? This is alpha. So here let's summarize this one. V out is equal to how much at the end? V maximum over 2 pi times 1 plus cosine alpha, and this is the average output voltage for the half wave controlled rectifier with R load, this portion. Now let's study the same thing here, but by changing the load. Okay, we will change the load from R load to be RL load. Here we have the same rectifier, half wave controlled rectifier. Controlled rectifier means what? We have a thyristor, okay, because we can control with the signal that's going to the thyristor. Let's study the waveform. Here we have the same thing. We have input voltage, a sine wave. When the input is positive, then what happens at this moment? The thyristor will be in the forward bias, right? But without signal, it will never work. Okay, so we'll wait until we receive the signal at this point. This is alpha, the firing angle. Until the thyristor receive the signal, then it will conduct. Once the thyristor conducts, then you will find that the current starts flowing inside the load. Okay, at this point, because we have RL load, you'll find that this current, the output current, will be delayed. Okay, will take time, because we said the inductor holds the current. It takes time. It's not instant change like the resistor. The resistor, we have current okay, we don't have current, then 0. But the inductor, no. The inductor takes the current, holds the current, and takes time to leave this current. So you'll find that the current inside the load, inside the inductor, it will be delayed like this. It will take time to leave the inductor. If you look at this point here, this is T over 2, you'll find that at this point, the voltage across the thyristor is equal to how much? Is equal to 0. So the input voltage is 0, but the thyristor will keep conducting. Why? Because we have current at this moment. You can see here we have current. So the thyristor cannot be off, will keep conducting until the current leaves the whole current leaves the thyristor, will be dissipated, and then you'll find that after the current reaches to 0, the thyristor became what? Became off. So at this point, the thyristor is off. Here, from here to here, thyristor is on. Although at this point, the input voltage is 0 or negative, but because we have current inside the thyristor keeps conducting. Why this current? Because the output load. The load is RL load. We have current inside this load. So this is the behavior of the current and the voltage within the half-wave rectifier with RL load. This is very important. If we have current, then all the rules will be changed. Now let's have a look at a load similar to this, but with a battery. We have L load and a battery. For example, you want to charge a battery or so. So here we have the same behavior, but we need to make sure that we take into consideration the voltage difference. If this is 100 volt, for example, then you have to make sure that the voltage across the thyristor must be larger than 100 volt. Okay, otherwise this will not conduct. So look at this point here, for example. Again, the firing angle at this point, this is alpha. This is the input voltage. When the input voltage is positive, nothing will happen. When the input voltage is greater than the 100 volt and there is a firing angle sent to the thyristor, then at this moment you'll find that the thyristor will conduct. At this point, the voltage is 0, no difference. Also, we don't care also about the 0 line here, we care about the 100, right? So here, at this point, the voltage across the output is less than 100, okay? If this is a diode, then we expect that this is conducting, or if the output is not L load, okay, then this should be conducting, right? But because we have L load, we have current here, we have current inside the thyristor, so this will keep conducting. Once the current is 0, you'll find that the output voltage will jump to 100 volt, okay, the battery voltage, okay, and so on. And this will keep waiting for the next cycle until we reach to the, until we have the firing signal, then we'll conduct again. So from here to here, the thyristor is on, conducting. Otherwise, it will be off. So the only difference in this, when we have a battery, we need to think about the voltage difference between the input and the output. So you'll find that the output, as if it's shifted by 100 volt, by the E volt. And here, of course, if you look at the thyristor voltage, it's easy, just the input voltage minus the output voltage, you will get this shape. So let's move to the next topic, which is a single phase full wave rectifier. Now we'll talk about the full wave rectifier. So here we have the single phase full wave controlled rectifier with R load. Okay, here we have R load. Okay, it's the simplest case. For the full wave controlled rectifier, when the input is positive, we will send signals to thyristor 1 and thyristor 2. So at this point here, alpha, we will send signal to thyristor 1 and thyristor 2. Okay, when the input is positive. When the input is negative, so you will send signal here. So this is alpha 1 and this is alpha 2. This will be signal to what? To Thyristor 3 and Thyristor 4. So at this moment you will send signal to Thyristor 1 and 2. At this moment you will send signal to Thyristor 3 and Thyristor 4. If alpha 1 and alpha 2 are same, so we can say this is just alpha. If they are different, we will have to say this is alpha 1 and this is alpha 2. When the input is positive, we send signal to Thyristor 1 and Thyristor 2, and you'll find that the output voltage, it will be how much? It will be similar to this portion. This is the output voltage. It will be conducting after we send the signal. Even though the input voltage is positive, but without signal, Thyristor 1 and 2 are not conducting. On the negative half wave, same thing. Once the Thyristor 3 and 4, because they are in the forward bias in the negative half wave, then you will send signal to Thyristor 3 and 4. They will conduct after they receive the signal. Okay, and you'll find that the output will be, again, it will be this wave form. Now, because we have R load, okay, so definitely the voltage and the current will be in the same shape, no problems. And the Thyristor will be off once the input voltage hits the zero line. And again, the input current here, it will be distorted like this. So this is the input voltage, but the input current will be distorted. It will not be a sine wave, for example. So the current on the input is distorted, and also here we have to make sure that we have some adjustment to make sure that the harmonics are minimum. Now, if we try to find the voltage on the output here, we care about the average voltage of these portions. So if you try to find the average voltage for this portion, you will find that V out is equal to how much? Now we have this from 0 to t over 2, right? And the integration from t1 to t over 2. Then after that is a repetition, right? So we can only find the average for this portion, right? So here we can say that 1 over t over 2, right? Integration from t1 to t over 2 for V maximum sine 2 pi t over t dt. And then this integration for sine, again, it's minus cosine. And this will be from t1 to t over 2. V maximum will go out. And this will be divided by 2 pi. So 2 will go with 2, and here we're left with pi. Okay, V maximum over pi. Again, this will be 1 plus cosine 2 pi t1 over t times V maximum over pi, and this is alpha. So this V out will be equal to how much? The average, it will be how much? V maximum over pi times 1 plus cosine alpha, the firing angle. Now we have studied the half-wave controlled rectifiers with few loads like R load, RL load, L load with battery, and also we studied now the single-phase full-wave controlled rectifier with R load, the simplest case, R load. Also we obtained the average voltage for both half-wave rectifier and the full-wave rectifier with R load. And we studied the firing angle. We have now like knowledge about what is the firing angle, what is the effect that firing angle can do within the Thyristor circuit. You'll find that last time we don't have this factor. Alpha is not there when we have a single phase full wave rectifier, but here we have alpha within the equation. So this alpha will decide how much voltage I can transfer from the input to the output, right? So I have power to control the output voltage. I'll stop here for this lecture and I'll see you in the next lecture.